Imagine trying to find the roots of an equation with, I don't know, 17 powers of x. It's huge.
It really is. And the standard tools we usually reach for, things like, say, Newton's method, they're clever, definitely useful for getting close, but they mostly give you approximations.
Approximations, right. So subject to rounding errors, things like that. You don't necessarily get the dead on exact answer. And wasn't there Abel's theorem? Doesn't that sort of say some of these are impossible to solve exactly with radicals?
Exactly, that's the classical understanding. Abel proved that for polynomials of a degree 5 or higher, there's no general formula using just addition, subtraction, multiplication, division, and roots, radicals that will always give you the exact solutions.
So the textbooks kind of say, good luck getting an exact answer for some of these big ones. But, well, that's why we're here today. There's apparently a new approach, something called Ezouidi's theorem.
That's right. It's positioned as a completely different way of looking at it. A method that claims to deliver exact symbolic solutions, even where classical ideas suggest it's impossible or impractical.
Okay, exact symbolic solutions. That sounds like a pretty bold claim against the backdrop of Abel. So our mission today is to really get into this theorem. We'll use a degree 17 polynomial as our example, apparently, and see how this method stacks up against the traditional ways. Let's dive in.
It's definitely a fascinating challenge to the established view. You have centuries where the difficulty of finding exact roots for these high-degree polynomials was, almost taken as a given. People accepted that beyond degree 4, things got messy. You relied on numerical methods, finding values that were close enough for practical purposes.
Close enough, but not perfect. And that close enough can sometimes matter a lot, right? Those small errors can build up.
They absolutely can. And Abel's theorem really cemented that idea. It wasn't just difficult, it was proven that a general radical solution didn't exist for degree 5 and higher. So the focus shifted heavily towards approximation techniques.
Okay, so history points towards approximation being the main route. How does Ezouidi's theorem step around that? Does it just ignore Abel's theorem?
It's maybe more accurate to say it operates outside the specific constraints that Abel's theorem addresses. Ezouidi's theorem isn't looking for a solution purely in terms of radicals in the classical sense. It uses a different framework altogether. It directly claims to provide precise solvable roots, even for cases that fit Abel's criteria. The key difference is the method. It's about systematic, symbolic derivation, not approximation or just radical expressions.
A different framework, okay. So it's not trying to do the impossible within the old rules, it's sort of changing the rules or using a different rule book.
That's a good way to put it. It approaches the polynomial differently from the start. It doesn't rely on iterative numerical methods. Instead, it focuses on breaking down the polynomial structure symbolically.
How does that work, practically speaking? How do you break it down symbolically?
Well, at its heart, it involves a recursive process. You calculate a series of special coefficients derived from the original polynomial's coefficients. There's a formula, obviously quite mathematical, but the concept is about using things like binomial coefficients and powers recursively to define these new symbolic values. Let's call them skests.
Tests, yeah. Okay. And these aren't numbers yet, they are symbols, expressions.
Exactly. There are symbolic expressions derived from the original polynomial's coefficients. Each is calculated based on previous ones and the original terms. Crucially, no approximation happens during this calculation. It's purely algebraic manipulation.
Right, keeping everything exact from the start.
Precisely. And for the degree 17 example we're using, the calculation of these scuff values yielded some very interesting results. The source shows that many of them actually turn out to be 0.
Oh, which ones?
Specifically, 0 through S6 were 0, and then S8 through S14 were also 0, and S16 as well.
Wow, that's a lot of zeros. That must simplify things quite a bit.
Enormously. It tells you that the underlying structure, when viewed through this lens, is much simpler than the original full polynomial might suggest. The complexity is sort of condensed into just a few key non-zero values.
So which ones weren't 0? Those must be the important ones.
Correct. For this specific polynomial, the calculation showed that S7 was connected as 24309 times 17 to the power of 8. And S15 was 533044024 times 17 to the power of 16. These are exact symbolic values.
Okay, that's your 20309 times 17 to the 8 and 5324024 times 17 to the 16. Big numbers, but exact. So you have these S values, mostly 0, a couple non-zero. How does that help solve the original massive degree 17 polynomial?
This is where it gets quite elegant. Because so many sex terms are 0, the polynomial, when expressed using these terms, simplifies dramatically. Instead of the long, complicated 17th degree expression, it collapses down to this. px equates multiplied by 16 plus s7r by 8 plus s15r exceeds 0.
Whoa, hang on. Just x times by 16 plus s7r by 8 plus s15r. That looks much, much easier to handle.
It is significantly easier. And look, right away you can see one solution.
Yeah. If the whole thing equals 0 and it's x times something, then x equals 0 has to be one of the roots. Simple as that.
Exactly. An exact root identified immediately thanks to the simplification.
Okay, so that's one root down. What about the by 16 plus s7r by 8 plus s15r equals 0 part? That still looks a bit scary with powers of 16 and 8.
It does, but look closer. What if you think of by 8 as just some variable? Let's say y. So y equaled by 8. Then what does by 16 become?
By 16 would be by 8 too, so.
y2.
Oh, I see. The equation becomes y2 plus s7r y plus s15r is 0. That's just a quadratic equation.
Precisely. It's essentially a quadratic equation in terms of by 8, and we definitely know how to solve quadratic equations exactly.
Using the quadratic formula, yeah. Mm-hmm. Wow. So you solve for y, which is by 8, using the formula with s7r and s15r.
Correct. You calculate an intermediate term, s1r, which relates to the discriminant in the quadratic formula, involving s7r and s15r. Then you find the possible values for y, which is by 8. And from there, finding the values for x involves taking the 8th roots.
And because all the Nace values were calculated symbolically and exactly, the solutions for y, and therefore for x, will also be exact symbolic expressions.
Exactly. They often involve complex numbers and roots, expressed precisely, perhaps using complex exponentials, but they are the exact solutions. No approximation needed at any step.
That really is the core advantage then, isn't it? Moving completely away from approximation, you get the mathematically pure, precise answer.
That's the fundamental claim and the power demonstrated in this example. Where classical methods often hit a wall for exactness or rely on numerical techniques with inherent error potential, this method provides a pathway to exact symbolic solutions.
Even for something like a degree 17 polynomial, which sounds incredibly daunting otherwise, the simplification step seems almost magical.
It highlights how a different mathematical perspective, this recursive symbolic calculation, can reveal underlying simplicity. It bypasses the need for approximation by maintaining exactness throughout the process.
So the aha moment here is really the shift from being content with close enough to demanding and apparently achieving exactly right, even for these really tough cases.
It certainly seems to represent that kind of shift, yes. A move from approximation as the default for high-degree problems to the possibility of absolute precision.
And that makes you wonder, doesn't it? If this kind of breakthrough can happen in polynomial solving, what does it suggest about other areas? Other problems in maths or science or engineering where precision is absolutely critical?
It definitely opens up that line of thought. When something previously considered effectively unsolvable in exact terms suddenly becomes solvable, it prompts a reevaluation.
What other unsolvable problems might just need a completely different angle, a new theorem like this one?
It's a powerful question. It challenges us to think about the limits we perceive. Are they inherent, or are they just limits of our current tools and perspectives?
A really interesting thought to leave things on. If a theorem can reshape our idea of solvability right here in mathematics, maybe we need to keep questioning our assumptions about what's possible elsewhere too.
Well, this has been fascinating. Thanks for walking us through that.
My pleasure. It's certainly a thought-provoking development.
Indeed. Join us next time for another deep dive into compelling ideas.